Questions?
How was your conference?
The conference was excellent. What, did you hear something? No, it went really well. This is actually one of the papers that I gave, and I'm not going to give you the whole paper, but this is where we're at. So you have, we'll wrap up this week, right? No, this week we start a different experiment. And this is, historically what has happened is that we go through colloidal behavior, you know, and then we do the rheology thing, and all those things are connected. There's a lot of science involved, demonstration of that science. And then we would get to forming, okay? So we want to talk about, say, extrusion, all right, or tape casting, or even slip casting, right? Then what we do is we give you a recipe, and you go do it. Hate that, right? Then all this science and theory, and then when it gets to actually making samples, we revert back to basically the recipe approach. You know? Well, here's how you do it, you know. And there's a book. It's actually a worthless book. It's called Polymeric Additives for Ceramic Processing. Okay, it really is truly a waste of paper. All right. And this guy talks about, there's two editions, by the way, and if you compare edition 1 or edition 1, edition 2 together, there's not a different word in edition 2. They're exactly the same. The color of the book is different, so that must be the justification for the edition. All right, so he goes through all of this stuff about polymers, you know, organic chemistry, and when it gets down to doing tape casting, he gives you a recipe. And we've done a lot of work in polymeric additives because you have dispersants, you have plasticizers, you have binders, and they do not behave independently. What's a dispersant do?
Disperses.
It changes the interaction between the particles. Right? How does it do that?
Absorbing onto the surface.
Yeah, it absorbs on the surface. It does either one of two things. Either it creates a situation of steric hindrance, so the particles can't get together, or it creates a charge that provides you essentially an electrostatic interaction, which we call electrostatic. That's what the dispersant does. Now, what if I bring in, say, another polymer? What does it do? It does not typically ignore that dispersant on the surface of the particle, that polymer that's on the surface of the particle. It interacts one way or another. Okay, and there are three ways it can interact. It can either interact, say, where it's happy with that polymer on the surface, right? We would call that compatible. Or it would not like that polymer on the surface, so that it phase separates, right? So you're going to get regions in the suspension that are rich in polymer, and regions in that suspension, domains, if you will, that are rich in particles. It will separate. And the third case is that it forms what's called an associated complex. So it sort of acts like a different polymer altogether by its interaction with other polymers in the system. That is the interesting part of polymeric additives, is either predicting or measuring those interactions. Now, let's take a step back. We want to do extrusion, and we want to do tape casting, and we're going to do slip casting. So, where do we start? And the place that we start, it used to be that we started with a recipe, okay? We're not doing a recipe. What's going to happen over the next 3 weeks is that you are going to design the experiment, okay? This week in lab, so we have Tuesday, Wednesday, Thursday, weeks 1, 2, and 3, okay? There are 2 groups on Thursday, so that complicates our issue only a little bit, okay? So Tuesday, Wednesday, and Thursday, in the Tuesday lab, you're going to have 3 groups. One group does extrusion, one does tape casting, and then one does slip casting, all right? In week 2, then the group that did tape casting might do extrusion, right? Or the other way around, slip casting, extrusion. Then in week 3, you're going to do slip casting, tape casting, or excuse me, extrusion and tape casting. Follow? All right. What happens on Thursday is just a little bit different. Extrusion and tape casting and extrusion, and then slip casting, both groups do it the third. All right. So how does this work? You're going to go into the lab as a group, right? We'll have 3 groups in each lab. One group works on tape casting, one extrusion, one slip casting. You're going to design the experiment. You're going to execute the experiment in the lab. Then you're going to write up a short summary due next Monday of how that experiment is done. And that information is then transferred to the next group. And then they try it. And then they will make modifications and transfer that to the third. Does that make sense? Okay? And our goal is for you to design the experiments and execute the experiments, and then to develop, in each case, optimum body for slip casting and for tape casting for extrusion. Does that make sense? Okay, now, how do we do that? Which is not based on just trial and error and let's hope, come up with a recipe. What we do is we use something called a specific volume diagram, okay? So specific volume diagrams were first introduced by George Onoda in 1983. And he wrote the paper, Drilling American Traffic Society says, opportunity, something like that, specific volume diagrams for ceramic processing. Sounds great, okay? I'm thinking that, I'm trying to figure out the reference. I did. It's in on page 4 in section 5, probably, okay? And so he introduced the idea, and then nothing happened with it for roughly, what is this, 30-something years, right? And the reason that it didn't work, so what we do is that we plot, actually, 1 over density on the y-axis versus, say, water content on the x-axis. And you know that on a weight basis, so this is on a weight basis, it's essentially plotting a rule of mixtures. But you have 2 lines, okay? And where those lines intersect, okay, is your optimum. In other words, the amount of water necessary for the packed bed pore structure. So what you have is this, okay? This is weight percent water, okay? And this is 1 over the density of your powder, we'll call it alumina, and this is 1 over the density of water. Good? So that specific volume is 1 over density. So I'm going to start up here, and I'm going to say, okay, this is 1.0, 1.0, here is 0.5, and here is 0.25. Okay? So this value, right, is 1 over 4, which is the density of aluminum. That's your skeletal density. Good for that? All right? This is actually 1 over the density of water, right? Which is equal to 1, conveniently. All right, now, last class, I brought in the golf balls and the BBs, right? Was it last class? And when I was here. And so when I added the BBs to the packed bed of golf balls, what happened to the total volume of the system? Stay the same. So that means that my change in density, or change in volume, not change in density, change in volume was 0. So if I added a golf ball to a packed bed of small particles, right? So if I have this and I have small particles in here, right? And I add a golf ball, what is the change in the volume of the bed? It's the volume of the golf ball. Does that make sense? So if I add this in here, the total volume increases by the volume of that golf ball. Okay? You good for that? It makes sense, right? If I take water and I add a chunk of alumina to the water, the increase in volume is the volume of that chunk of alumina, right? We actually use that as a way to measure density. That is essentially Archimedes' principle, right? When we measure density, it's called immersion method, not Archimedes' method, okay? Archimedes method means that you measure the volume of overflow water. We don't do that. Now, if if you have a bunch of slaves or servants running around, which I have neither, okay, and you fill a bathtub to the brim and then you sit in it, right, you're going to pour all that water on the floor, which is then someone else's problem to clean up, right? But the volume of water that you pour out on the floor is the volume that you occupy. I remember they did this with baseball players a few years ago to figure out body mass index, and whether they had fat or whatever. So we don't do that. We essentially look at the buoyancy in order to determine the volume of the sample. But if I add, so I get a line on this curve, and it's going to go to this value, because this is then the increase in volume is actually the volume, specific volume of that particle. So my line looks like this. Okay, that's the first line. The second line, if I add water to the packed bed, what happens to the total volume? No change in volume. So the question is, what's the density of the packed bed of particles? Density of the packed bed? 50%, right? Told you, remember that value before, right? 50%. Density of the packed bed is 50%. Good place to start. What is the density of a 50% packed bed of alumina? 2. And the math works out somewhat inconveniently. 1 over 2 is 0.5. You good with that? Sorry, they're all the values that we talked about today are 0.5. So if I go from here, but the increase in volume associated with adding water to that packed bed is 0, so my line goes like this. This intersection point represents the maximum density in the system, right? Or the minimum specific volume. Does that make sense? Okay? That is where this pore volume is filled with water. Good? That is the idea behind the specific volume diagram. Now, what you get here is that so what you can get at this point is how much water is necessary to fill that pore volume on a weight basis. Okay? That sounds like a good idea. It's not. All right? Why is it not a good idea? Yes, we do everything by mass. Why is that value on a weight basis not a good idea? Let's say that, what do you think that value is on a weight basis? 20%. How do you know that? Well, because density of water is 1, right? The pore space you have is 50%. If you do the math, okay, and you look at the weight percentage of aluminum, etc., okay, you get the density of 4, that works out to be 20%. You can do the math. 20 weight percent water. Why don't I like that value? What's wrong with this picture? Let me take it a different direction. You leave here and you go work for a company, right? They make ceramic components. Is everything they make out of alumina? No. What if I make it out of zirconia? What if I make it out of sodium carbide? What if I make it out of clay or porcelain, right? What happens is that the density of my powder is changing. Good? What's the packing density of zirconia? Good. What's the packing density of sodium carbide? Oh, you're good. Okay? So I call him because he says 50% no matter what I ask for some person. All right, so, but you understand though that if I pack zirconia for 50%, the amount of water necessary to fill that pore space is 50% by volume. It's not 50% by mass because the density of zirconia is different. So what happens? If you look at recipes, we should make this a homework problem. Go find recipes for tape casting alumina or sodium carbide or zirconia or barium titanate. They're all different. All different because the density of those powders is not the same. So when you look at those recipes, you would look at it and say, wow, the zirconia recipe is much different than the aluminum recipe, right? Zirconia must behave differently than aluminum. And I would argue that that is not the case, nor should it be the case. What I'm looking for is I think that all extrusion processes should require the same rheology, the same flow behavior to extrude properly. Reasonable? Did you ever play with a Play-Doh machine? Right? I mean, you put the material in and you basically extrude it out through a star-shaped die or whatever it is, right? But you have a certain plasticity. That plasticity is what is necessary for that material to flow out of that extrusion die. Okay? If you go into the mud lab and you extrude a porcelain body, you have a certain window for plasticity that works. If it's too dry, it doesn't extrude. If it's too wet, it's sloppy, right? It doesn't hold the shape. So how do you define that window? And you do it through specific volume diagrams, but not on a weight basis. Okay? So what we do is we say, we don't like this rule of mixtures. Mass fraction basis, nope. You can take that out of the picture, okay? And what we're going to do instead is we're going to look at it on a volume basis. Now, it's not linear, but I'm going to plot specific volume, which is 1 over the density, it's this U shape, versus volume percent, okay? What I'm going to do is I'm going to cheat because I can, and I'm going to say, okay, we're going to ignore this down here on the end. And I'm going to take this value, right, which is now the density necessary for pore filling. I'm going to come over here and say, this is my maximum density of the system, right? And then up here is 1, and at this point, this is pore saturation. Good? What's that point? 50%, see? We're on a roll here. All right, so is that different for zirconia or silicon carbide? No, it's not different for alumina either. That means all of my curves will start at this point. Now they may start at a different specific volume depending on the density of the powder. Don't care about that, okay? But again, it's a curve, exactly like the curve that's shown there. Looks like this, okay? And what we find is that for all extrusion, or all systems, all ceramic forming systems, outside of dry pressing, start with pore saturation. In other words, the first place that I have to go is to fill the pores with water or some other liquid. It could be water plus plasticizer or binder, okay? We typically ignore the dispersant because it is not free in solution, right? The dispersant is absorbed on the surface of the particle. So it isn't really a part of the bulk fluid, and the volume is exceedingly small, so we ignore the dispersant, okay? The total amount of liquids where we start is to fill the pore volume. And then we're going to add excess liquid on top of that pore volume to hit our window for extrusion, or tape casting, or slip casting. Does that make sense? Okay. What changes my pore volume?
The density,
Of?
the powder.
No, we're talking about volume, right? We're talking about pore volume, not the density of the powder, right? How can I change, how can I make my pore volume smaller? In other words, how can I pack my powders more efficiently?
Different size.
2 different powders.
Okay, like particle sizes, okay? If I disperse the particles, they will pack to a higher density compared to flocculated, okay? You should get that out of your sedimentation tubes, right? What else can I do? I might be able to change the shape of the particle or have a different shape. If I have flat plate-like shapes, they might pack to a higher density than spheres, for example, right? So I have different techniques for changing the packing efficiency of the powder. Are you good with that? All right. But I'm pretty much stuck with wherever I start. So if I start with A16 and I'm not blending particle sizes, I'm going to have a certain packing efficiency that is based solely on the degree of dispersion. Okay? If I disperse the system, my packing efficiency increases. If I flocculate the system, my packing efficiency decreases. That means that where I start here, my pore volume, where I start will be different. Okay? If I pack more efficiently, or let's do less efficiently because it's easier, I might start here, and then this is pore saturation, then my curve does this, or whatever. Okay? Roughly like that. All right? But I start here. So now, if I look at an extrusion system, can I then define a window for extrusion that works? And this is just a portion of that curve. But here's my saturation pore volume. Notice that there are no numbers on the x-axis. Okay? That's intentional. This is a cartoon. Right? There are no numbers on the x-axis because I need to know that value, but globally, everything behaves exactly the same way. I fill the pore volume, and then I'm going to have an amount of excess liquid on top of that necessary to fill the pore volume. And if I hit that window, it's 6% excess liquid plus or minus 1.2%. So you could say that I'm between roughly 4.5 and 7.5 excess volume of liquid necessary for extrusion. You get that? I do not care what powder you are extruding. Okay? All systems that we have looked at up to this point are showing me that I need 6% excess liquid to extrude. If I grade the particle size distribution and I get higher packing efficiency, this pore volume changes, but my extrusion window does not. The excess water over that necessary to fill the pore volume stays the same. I'm still 6%. Okay? So if I make my packing more efficient, I'll move this around, but this relative relationship of that window to my pore volume is fixed. Is that good? If I change degree of dispersion and make it more dispersed, then that window stays the same. And then for tape casting, it's 10% plus or minus 1. Okay? So tape casting is a competition process, right? You want to have enough water in the system for flow, but you don't want to have a lot of excess water that allows the particles to settle out while it's drying. And you also can't handle a great deal of shrinkage, or else your tapes will curl or they will mud puddle crack or whatever. Okay? And if you have enough excess liquid in the system, so you have a tape like this, right, your thickness, and you end up with the particles settling, your large particles will be on the bottom, your small particles on top, okay, and your packing efficiency will not be the same because you've segregated by size, and the system will curl. It will warp because you have a difference in gradient. And then you have this shrinkage from your tape thickness to your final thickness, right, because of that excess water. So that's why we define a window. Can I tape cast with more water than that? Absolutely. It's just not going to look very good. Okay? And this window, okay, this 10% plus the pore volume is anything I put in the system. It could be plasticizers, things that are supposed to interact with the binder to help it become flexible or stay flexible. You have the binder itself, okay? You have the water. You add the volume of all three of those things together, that's your total volume, okay? And the total volume is the pore volume plus your excess volume. That's your total. So now, hopefully you can see the problem. If you look at a recipe, right? And the recipe, you look at one recipe and it tells you so much binder, so much plasticizer, so much water, and then you have your aluminum. And you look at a different recipe, you have so much plasticizer, so much binder, so much water, but you have zirconia. Those numbers don't appear to line up, okay? Because you have to pack powder and fill the pore volume first. So what happens is, what if I have, say, working in a factory and I have a lot of raw material, a lot, not I have a whole bunch, but I have a lot comes in from the raw material supplier. and I have a certain packing efficiency. The next batch of powder comes in, has a broader particle size distribution than the one I currently have in production. What do you think happens to my packing efficiency?
Increases.
It increases. Oh, if the packing efficiency increases, then that means the amount of pore volume I have is decreasing. So now what happens is I make the same batch up for extrusion, and it's sloppy. Because my packing efficiency, I only have a window, 6 plus or minus 1.5 or whatever, right? And so if my packing efficiency goes up by, say, 2%, suddenly I have 2% more liquid in the system than I had in the previous batch. And now I could even have moved right outside of my extrusion window. You see, that small a change can dramatically change my manufacturing process. Good? Okay, so that's where we're headed with this. So what we have is, you are going to then construct experiments to define that window. You're given the window, my gift to you, okay? There's the window. You have the window, right? Question is, how do you determine then what a tape casting body would look like, or an extrusion body? And what about slip casting? What do we do then? What do you think about slip casting? So, make a slip cast sample, right? And let's say you're making a simple cup shape, okay? Pour your slip in, and then you build up a wall thickness, right? And then you pour out the excess. It's called drain casting. What contributes to that? In terms of our discussion of specific volume, what do you want to have happen?
Particles to settle.
No, you do not want the particles to settle. You are absolutely right. You do not, right? What do you want? You would like probably the most efficient casting, right? Shortest casting time to get the wall thickness that you desire. Good? Okay, we'll talk about it more in the next couple weeks, but you would really like to have the highest possible solids loading that will flow, so when you pour it into the gypsum mold, the capillary suction that pulls the water out builds a wall thickness quickly, and you have a short casting time, right? So you really want to be as close to pore saturation as you can, but you still have to be able to drain that suspension and pour it. So you might be that your slip casting window mimics your tape casting window, but recognize that I could go up to very dilute suspensions and still slip cast. The problem is, instead of getting a wall thickness like this, I get a wall thickness like this, right? And now I got to cast for, from today until like sometime on Thursday to get a desirable wall thickness. Okay, so that's the other aspect of this in terms of the specific volume diagram. Can we define, and I have not done it for you, can we define the window for slip casting as well? Okay, are you good with that? That's what happens this week. So, what do you need? Let's do that. What piece of information do you need in order to start your experiment? This is sort of a call and response question, and then you answer. So, what piece of information do you need to start your experiment?
Pore volume basis.
You need the packing efficiency of the powder, right? From that, you get the pore volume. How do you get the packing efficiency? So, when we do the specific volume diagram, let's just draw that for giggles for the moment, okay? We'll do the weight percent because it's easy. Here's water, right? And it goes down to this. This is 1 over the density of the powder. So there's my first line, right? How do I get my second line? Oh, I told you that here's 50%, So I started here and I did this, right? And I say this is 50% packing efficiency. And from that, I get my pore filling optimum on a weight basis, all right? When you did the lab last few weeks, right, or before the break, you have A16. What's the packing efficiency of A16? I'm not calling on you because it's not 50%. What is it? I told you to measure it. Yes, I did. You started off with 280 grams of A16, right, in a beaker. What was that volume? It's about 350 cubic centimeters, right? You had 130 milliliters of water, right, that you're going to put this huge volume of powder in. Look, I know we talked about this because this is cool, and I talk about it every year, and I know I talked about it with you at least twice, all right? What's the packing efficiency of A16 dry? %, times 4. 0.8 grams per cubic centimeter. This is 270 divided by 350 is 0.8. Okay? You were packing that particle to 20%. That means that if you were to do this dry, your point's up here, right? And if you do this line, you would say that your pore filling is now this huge amount of water, right? What happened? Where have I gone wrong? Because to measure the packing efficiency of the powder, you must be measuring that packing efficiency under the same conditions that you're going to do your experiment. If you're going to disperse the system, you need to measure the packing efficiency of a dispersed system. If you're going to reflocculate it, you need the packing efficiency of a flocculated suspension. When you add water, what happens is that this comes down like this, okay, to that point. If I look at the packing efficiency of my powder and I get 50%, that's because I'm in water. I cannot measure the packing efficiency of that material dry. All right? Because it's not the right packing efficiency. As soon as I put in water, my packing efficiency changes dramatically. And you are going to do forming processes in water. So, we have a slick way of doing this. And we get our packing efficiency by slip casting. Okay? So you would make up a suspension, right? You want it to be flocculated or dispersed? All right, so let's make it dispersed. Make up a dispersed suspension, and you cast a pellet. All right, we have a bunch of molds. Typically look like this. They're Lexan or plexiglass, and they have essentially 25 holes in them. And I can draw all these on here, but I don't need to. And then you get out of that a little pellet like this. It's roughly about a ½ inch in diameter, something like that, right? And roughly a ¼ inch tall. Okay? Now, there's two things you can do at this point. You can do what we've historically done, and you can dry that sample, and then you can measure its volume and density through an immersion method using kerosene, royal paint. We'll teach you how to do it, but not this week. We figured out a slick way of doing this. So when I cast that, what do I have? I have a packed powder bed, and when I get done casting, the pores are filled with water. Correct? So if I take this pellet and I weigh it right out of the slip cast mold, okay, I get a saturated mass. Good? If I dry that pellet and I dry all the water off, what do I get? A dry mass. Okay? So saturated mass is S, actually it's W in ASTM. For wet, this is dry. W minus D equals what? Mass of the water. Okay? What's the volume of the water? Oh, it's equal to the mass of the water, right? Because the density is 1. What is D?
Mass of element.
It's the mass of the powder, right? What's its volume?
4.
It is D divided by density equals volume of alumina. Okay? So the dry mass divided by the density gives me the volume of alumina. Volume of water plus volume of alumina equals the total volume, right? Volume of alumina divided by the total volume gives me my packing efficiency. Right? So this value here, the volume of water divided by the total volume, gives me the pore volume.
So for total volume, we just calculate it from the size of the pellet?
No, total volume you get from the mass dry plus the saturated minus suspend minus dry. Volume of water plus the volume of powder is your total volume. You've not seen these slip cast pellets before, but they typically, although they do, my drawing here, as perfect as it is a nice right circular cylinder, and it's never cased. There's always a little meniscus on the top, etc. The other thing that's kind of cool about this is you cast these, okay, and you take them out of the mold. You don't let them sit around. What happens if they sit around? Say again? They lose water. What does that do? It skews your data. The volume of alumina stays the same. The mass of the water decreases. It affects your total volume. Your total volume appears to be smaller. You then estimate a higher density for your packing efficiency than you actually have. That screws up your pore volume starting. Okay? I would think one of the experiments you might do is to determine how sensitive this test is to time after casting. You understand? So what you do is you take your pellet right out of casting and you weigh it.
So just how long would you wait after casting? You pour it in and wait 5 minutes or something? Or
You wait until there's no more fluid, no more suspension left on the top. Flocculated casting is quick. What's your time?
About 10 minutes.
Yeah. Dispersed casting is slow. I'll show you why in a minute. But you cast, pull your pellet out. You don't care if the pellet's fallen into pieces, right? Because it's the total mass that you care about. You get the total mass. Leave it sit on the counter. Go back and measure it after 10 minutes, or 5 minutes, or 1 minute, and then plot that. How fast does that water content decrease? And that water content decreases based on the available surface area of the pellet, not of your powder. Because if I break this up and have small pieces, I have a lot of surface area, my evaporation rate goes up. Okay? What's your window look like? How sensitive is that measurement to your window? Okay? Noah did this yesterday for you as a starting point. Here's his data. So we had 2 cases, A16 dispersed and flocculated. And then what he has is, he has the dish data in there, which you don't really care about. You got to tear that out though. If you leave the dish data in there, it looks really strange. Okay, so you got to measure the dish that you use, and then your sample, and then you get your saturated sample here, saturated mass. Okay. Then you dry your sample. That gives you the mass of the water. And these are all different, so you can't average the mass of the water. You can only average after you've normalized the data. You understand? So I don't care about the mass of water. If I have a big pellet, I have a large mass of water. So that doesn't make any sense. So what I get then is the volume of alumina and the volume of water. Those two added together, divided by this, divided by the, divided by density, gives me my packing efficiency. So what he finds is that for slip cast, he has an average of about 59%. Okay? So it's not 50%, it's about 59%. He has a relatively large standard deviation, 59% plus or minus 4. Why?
Because for the dispersed, they were taking so long to dry that
To dry or to cast?
to cast.
Yeah. Okay.
That I had slop.
So there's a couple ways around that. You could cast, decide to stop, screed off the top of the pellet that's still suspension and measure what's left. You follow? So you're gonna pour this in here, and the material's gonna cast. It's gonna take time, but you just pull the pellet out, scrape off the excess liquid, and weigh that and go with that. Okay? That was speed up. And here he gets, for the flocculated, he gets 47% plus or minus 0.8. Okay? So flocculated gives you then a larger pore volume than dispersed by a significant amount. So at 53% pore volume in flocculated, I'm roughly 40% pore volume in dispersed. Okay? So when I start my experiment, that's my starting point. And then I figure out how much excess liquid I need on top of that necessary to fill the pore volume. Good? So, let's talk about casting just for a second. There is a lot of bad casting data out there. So if you look at this, time versus thickness of your cast, the curve looks like that. Okay? And what people have done, and this is not correct, is they're going to fix their time, and they look at this value, and then what they do is they go back to 0. They go, that's my casting rate. So you have thickness divided by time. What's wrong with this picture? Say again?
It's changing.
It's not linear, and we were approximating as linear. What do you need? Oh, wait a minute. If I plot this in a different manner, square root of time versus thickness, straight line. Okay? So what you find is, this might be for flocculated, this might be for dispersed, that the casting rates for dispersed are much, much slower than for flocculated because the particles are packing more densely in the dispersed, with evidence of that here in terms of the density values, much more tightly packed. Therefore, water is going through a smaller pore size, and therefore there's more drag, hydraulic drag in the cast layer. That slows down that casting process. Okay? And so you get a much slower cast with dispersed. How do you get around the problem? How can you speed up the casting rate for dispersed? You go to higher solids loading, right? Make a more highly concentrated suspension. Casting rates would be, your casting time would be shorter. You could also cast a smaller pellet. Okay? So, I would like you to figure out, as part of your experiment, what that time interval would be after you cast before you measure. Okay? Because if you wait too long, then your densities will creep up. So you can show what that weight loss is as a function of time, because that's an important part of our experiment. And then the question is, how do you construct these experiments to do extrusion and to do subcasting and to do tape casting? And that is your job to develop. So you are going to design the experiments that you use for the next 3 weeks. Okay? The goal here is for you to get some more exposure to experimental design and implementation while learning how to do ceramic forming processes. Okay, now, if we were really good at this, what we might do is in week 3, maybe we give you a different powder. Right? Say we bring in zirconium, or we bring in, say, silicon carbide. Can we do the same thing with a different material? Okay. TAs will go over with you how you do the extrusion part. You have a tape casting setup, how you would do that. They'll walk you through all of that. And then you need to write up your experiment at the end for the next group to try. Is that good? There's one other thing. For extrusion systems, you work with a flocculated suspension. You are welcome to try a dispersed suspension. Okay, it typically doesn't work well. And the reason is that flocculated mass is a compressible system. Dispersed mass, because particles pack so highly, there's no compressibility. Okay, so it doesn't work well. For tape casting, we prefer to be dispersed. So that improves the quality of the tape and elimination of defects. There's one last question, okay? So we talked about binders and plasticizers, and for tape casting, you have to use a binder because the material itself, you can cast the tape, but it's extremely brittle because there's nothing holding it together. So the question is, what is the density of the binder solution? Okay, so if you measure the density of the polymer, right, that density of the polymer is not the density that the polymer will have once it goes into solution. Does that make sense? Okay, so you're going to measure a low density, and if you have something made out of plastic and you throw it in water, what does it do? It floats. Why does it float? Because its density is lower than that of the water. If you make a solution, though, you don't know what that density is. And the question is, does the polymer in solution create a different density solution? And that affects your volume in the specific volume diagram. So in the lab, we have, you'll see them in the lab, you have already, there's a bunch of graduated cylinders sitting around with funny colored fluids in them. We are measuring the densities of polymer solutions. And that's how you do it. You make up a polymer solution with a known amount of polymer in it, and then you weigh it, and then you put it in a graduated cylinder and get the volume. Good? And that will give you the density. It's very likely, because our polymer solutions are relatively dilute, that you have no correction for density. Okay? If you were in a more concentrated condition, then you have a correction for density. All right? The other thing you should do is calibrate the graduated cylinder. What does that mean? It doesn't mean you rub the numbers off the side of it, you're not. Okay? How do you calibrate a graduated cylinder?
Check against the polymer get plus.
Well, you could do it with the mass of water, which would be easier, right? If I have 100 grams of water, what's my volume? Oh, okay. If I have a 100 milliliter graduated cylinder, I can weigh 100 grams of water, put it in the graduated cylinder, and see where it falls. I had a senior thesis student once did specific volume diagrams with alumina. He came back, and none of his measured values matched his calculated values. Because his graduated cylinder, when it said 100, it was actually 96, or 8, something like that. So then all his volumes were off, and he corrected all that on his data. So you should calibrate the graduated cylinder, look at your polymer solutions on the side. Good? That's this week, okay? And next week and the week after. Specific volume diagrams is a way to predict ceramic forming processes. Any questions? You have a homework assignment associated with this. When's it due?
Friday, next Friday.
No, it's got to be this Friday.
This
You need to
Friday.
do the homework assignments on specific volume diagrams. If you have questions, you can ask on Thursday, you can ask the TAs. But it's asking you to calculate the specific volume diagram. Okay? And do those calculations so you understand what's going on.
We have your guys' lab, we need reports, I think the average on this one is like an 81 or 82, so much better than
So 67 or 89? Yeah, that would be the nine.
good, it's not. It's not so much. It's not better. You can rest your day.
Good.